My name is Alastair Rucklidge. I'm from the School of Mathematics in the University of Leeds, and I work in the area of nonlinear differential equations. Today I'm going to be talking about a technique called reduction of order, which is a technique where you can take, for example, a second order a differential equation and turn it into a first order equation, which then is easier to solve. It only works for linear equations, and there's one other price to pay, which you'll see as we go along. So I'll take as an example this equation here, which I've written up and labeled equation 1. It is x squared times y double prime. Remember, y double prime means d squared y by dx squared, plus x times y prime, so that's x times dy by dx, minus y, equals 2x, and our task is to find y, or the solution y, as a function of x. Now, you can see that it's a second order equation. It's got two derivatives here. You can also see it's linear because there's no products of y with y prime or y double prime squared or anything like that. So you might think that the technique that you've probably met, finding the characteristic equation, might work for this equation. But it doesn't, and the reason it doesn't is because the coefficients of the y double prime and the y prime are not constants, they're functions of x. So we could try it just to see how it works, and the way that that procedure works is we write down the homogeneous version of that equation, so that is x squared times y double prime plus x times y prime minus y equals 0, and I'm going to call that equation 2. And then we'll try y is e to the lambda x, where lambda is constant. And we'll try that, and we'll see if we can find a lambda that solves that homogeneous equation. So, to do that, we need to differentiate. So we get y prime is lambda e to the lambda x, and y double prime is lambda squared e to the lambda x. We put these into that equation, and we get x squared times lambda squared e to the lambda x. That's our y double prime, plus x times lambda e to the lambda x, and then minus e to the lambda x is 0. So that is our y prime, and that's our y. Now we've got a common factor here, which is e to the lambda x, and that is never 0. The exponential of something is never 0. So we can divide by e to the lambda x, and we get x squared times lambda squared plus x lambda minus 1 equals 0. And that would be the characteristic equation for this problem. But lambda is supposed to be a constant, and you cannot solve that equation for lambda without lambda depending on x. So this equation, this technique, will not work. If these had been just numbers instead of x's, then we'd have had numbers here, and we'd have had a quadratic equation for lambda, which we could have solved and then found a solution of the problem that way. So this won't work. What are we going to do? Well, let's erase that, and what we'll do is we will use this technique called reduction of order. Now, I mentioned reduction of order had a price to pay, and the price is that you already need to know one solution of this equation 2. Okay, so you already need to know y is something that solves that equation, and it turns out that y equals x is a solution of equation 2. So y equals x is a solution of 2. And you might say, well, where did that come from? Well, I've just given it to you, and that is the price that you have to pay for this method. You have to be given one solution of this problem. So now y of x, we're being told, is a solution of equation 2. And I'm going to verify that that is actually true. So if we're going to verify this, we need to substitute it into equation 2, and so we need to know what y prime is and what y double prime is. So y prime that's dy by dx, and y is equal to x, so that's equal to 1. And y double prime is the derivative of y prime, so that's equal to 0. Differentiating a constant gives you 0. So let's substitute these y double prime into here, y prime into there, y into there, and we get x squared times 0 plus x times 1 minus y, which is x. And that is indeed equal to 0. We've got 0 here, we've got an x, we've got a minus x, and that adds up to 0. So we're now confident that y equals x really is a solution of equation 2. Now, once we have that, the method of reduction of order proceeds by making a guess for y. And we're not going to guess y is e to the lambda x, that we've already shown doesn't work. So for reduction of order, what we're going to do is we're going to guess y is going to be some unknown function u of x times the function, the solution that we were told. So it's going to be times x in this case. And having made this guess for y, we will substitute that into the problem we're trying to solve. So we're going to substitute it into equation 1. So we're going to substitute that into equation 1. So just like we did a moment ago, we're going to need to know what y prime is, and we're going to need to know what y double prime is. So y prime is the derivative of this product. We've got a product of u and x. Differentiating a product, we get u prime times x, so it's the product rule, plus u times the derivative of x. Derivative of x we've already worked out is 1. So we can write this as u prime x plus u. And y prime, double prime is the derivative of this. So we've got a u prime times x again, so it's a product. We use the product rule again, so that will be u double prime times x plus u prime times 1. So differentiating this product, we get the derivative of u prime, which is u double prime, times x, plus u prime here, times the derivative of x, which is 1, and then we have to add in the derivative of u, so there's u prime, which we can bring together and write as u double prime times x plus 2u prime. We have a u prime here and a u prime here. Having got that, we can now put this expression for y double prime in here, and y prime in there, and y in there. And what do we get? Well, we get x squared times u double prime times x plus 2u prime plus x times, okay, so now we need y prime, which is here, so that is u prime times x plus u minus y, which is u times x, and all of that is supposed to be equal to the right-hand side of that equation, which is 2x. Okay, so what we've done is we've transformed a fairly nice looking equation here for y into something here which looks like it might be a bit grisly, but you'll see after we simplify things a little bit, we will be able to make progress with this equation. So I'm going to I'm going to erase this working here so far, but I'm going to save our y is u times x just up here in the corner to remind us what we're doing. And I'll proceed with simplifying that equation for you. And you'll see that we can indeed make progress with it.